So 3.1, then Valentina, maybe you can talk about 3.1. 3.2, you say you have vague idea, so maybe 3.1 is better. What? Yeah? Huh?
Like, I think we three have solved 3.2.
Okay.
And he really wants to be present.
All right. So some of you will go and show 3.2.
Okay. So we want for GLN, okay? Okay. These are reductive. And SL and K.
Sorry, can you change the white chalk? This is difficult to see what you are writing.
Okay, yeah. So as you, these are semi-simple. Okay, so we have this one. We have it like for free because Oshi, you already proved that.
Yes.
In the last seminar, using representation theory, you proved that this is simple. And we saw the last lecture that simple implies semi-simple.
Yes.
So this is done.
This is done. Yes. Okay.
And now, okay, but using this fact, we will get the reductivity of GL and K.
Okay.
On the following way. Okay.
I think use his way to prove that this is simple only work for complex number. Because he used the wave function.
Yes.
So you write K will be wave.
That's a good comment. I think you can say that your Lie algebra is semi-simple. Well, there is a way to. So okay, let's say that.
Yeah. Okay, but if I use that.
This is for K equals C.
Yeah.
Right,
This is
okay.
only for K equals C.
So we will maybe if you don't have K equals R, maybe we can discuss it after you. So that's it.
I can use another way different from K too.
Okay. So let's listen to.
Okay, so we can, because I also want to know. I was not careful enough. The sorry. So okay, you will tell me then.
Yes. Okay.
Okay, so this is just for C. This is simple. And okay, now we recall that GL and K. Just complex. I now realize that I just proved for complex. And this is scalar matrices here.
Yes.
So how can we write it? Just like this.
So you're using that SLNK is semi-simple, right? Each time.
To prove that this is reductive.
Okay.
So we know this decomposition, and we studied a theorem in the previous lecture that it was that if you have a Lie algebra, a Lie algebra G, and when we quotient by the radical, the radical of G, this is semi-simple. Right?
Yes, I agree.
And if there's another idea for which the quotient is semi-simple, then this ideal must coincide with the radical.
Solvable ideal.
Yeah, another solvable, such that the quotient is semi-simple, then
it coincides
with radical. So I will use that because I want to prove that the center the center coincides with the radical.
Mhm.
That's the definition of reductive.
Okay.
So I want to quotient by the center. I will not do the long computation, but
Mhm.
one needs to prove that the center of GL is precisely the scalar matrices.
Okay.
So if we quotient by the scalar,
Mhm.
we should obtain this part, S11. And since this is semi-simple, this is what we proved in the first step, then we use the theorem, the previous theorem.
Mhm.
Okay. Okay.
And CI is definitely solvable, like,
yeah.
because it's abelian.
Yeah, it's abelian, so it's solvable.
Mhm.
Then we use this result,
Mhm.
and we have that by uniqueness, well, when the uniqueness that this theorem is given us,
Mhm.
we will get that is reductive, because the center
Yes.
coincides with the radical.
Okay, so what would be an idea to show that this is exactly the center? Maybe we showed this a couple times already.
Yeah.
Yes.
Yeah, okay.
Yeah, I think maybe one needs to do the products and maybe taking particular matrices,
Mhm.
using the fact that it's for any matrix. We
Mhm.
can reduce our equations in some way, and to prove that the off diagonals must be 0,
Mhm.
and then work on the diagonal.
Yeah, so if you commute with some diagonal matrix with different entries on diagonal,
Yeah.
then this will give us that off diagonal entries of something in the center should be 0, right? Because when you multiply from the right, you multiply rows, and when you multiply from the left, you multiply columns, or maybe the other way around. But,
Or maybe
Yeah.
directly Schur's
Schur's lemma.
representation species SL. It's irreducible, and the action which is commutes with another action is the only way.
Yes, this is actually an elegant way to do this.
Okay.
Yes, okay.
Uh-huh.
So did we do it? Yeah, we proved that GLNC is reductive. Okay.
Okay, and now okay, wait, I need to think about UN.
Mhm.
I want to prove that this is reductive. So again, I need to think about the center.
Okay.
Okay, about the center of this algebra. And
It is actually UN
yeah,
or
the
UNR. UNC is something.
Yeah.
Yeah, it's just.
Yeah,
It's just entry. You mean the entry?
The entries can be complex, but it's a real
algebra, not a
algebra.
complex.
Yes. Okay.
Yep.
Mhm.
Okay. So.
Usually they don't write anything, just UN. But I mean, whatever. Mhm.
Like. That's okay. Indeed, that's why I just wrote like this in this part.
Yes. Okay.
Oh, what I was writing doesn't make sense. Okay. So yeah. At the beginning, I was thinking about this.
Mhm.
These were. Then I realized another way to do all these things, but I can say it later. We have something, decomposition like this.
Yes, you have this, right.
Because any matrix here, X,
So,
we can decompose it.
yes.
This is imaginary unit.
Right. So GLNC is a complexification of UN. That's
Yeah.
true.
And these are skew symmetric.
Mm-hmm.
These parts, skew symmetric parts. So, okay, I was using this to think about the. Okay, that's. Because I wanted to think about the center of UN. And we know the center of this, and we know this decomposition. So,
Yes.
because of this, we can see that the center of this thing would be just center here intersected with UN. We can prove that. Also, this,
okay, if you.
yeah, I proved this.
Okay.
So because of this, we will get that the center of UN will be the purely imaginary scalar matrices.
Okay.
So we get something. Write it like
But you can see it directly, right? That the center of UN is diagonal matrices in UN. Just using the same computations that you need to prove that the center of GLN is CI.
Yeah. Okay. Yeah, it can be done. And
Yes.
the first thing in my mind was in this video. So I have here like something like this. How can I say it? Like identity. Let's say lambda real number. So this is the way in which is the center.
Yes. Okay.
Of UN, right? Okay, so now.
So you're proving kind of a straightforward way, right? So you take the center and you would like to prove that this is radical as well.
Yeah. And okay, and actually we can think at the composition of this. We know this has two like parts. As UN is one part of this.
Yes.
The other like factor here is precisely this center. So we have something like this. And again, I think we can use the argument, the same argument as before. So we need to prove, we need to see that this is semisimple as UN.
Okay.
By doing the same argument. So we need to see that this is semisimple.
Yes. Okay.
Yeah. Okay, and for that, we can use the criteria that we saw about the forms, the bilinear form. That this is semisimple.
Okay.
If and only if the form is not degenerate. We can find a form is not degenerate.
Yes, you can find the representation. Semisimple. Yeah, you can do it with killing form. Sure.
Yeah. Okay. Oh, but wait. I'm thinking of maybe this UN. Well, I don't know if it would be necessary to use that precisely the killing. Maybe we can use another and to see.
If you use another one, which one?
This is reductive.
Yeah, it will say that it is reductive, right?
Yeah.
Actually,
So
this is
then-
how you can prove for everything here.
Yeah,
You can
so-
just take like tautological representation and consider trace form on it.
Yeah, so that will work also for
For
when
e-
we put
for
here
everything.
R or for anything.
Yeah.
Yeah. So yeah, because we take let's say a representation, and if we prove is non-degenerate, we saw that this is reductive.
Yes.
Yes, so we know that the center of these algebras will coincide with the radical, right? So we can do this for this case.
Yes.
The center coincides with the radical.
But for UN, you mean? Okay. But you still have to check it, right?
Yeah. Okay, so we can take which one? So is that
Just a tautological one.
yeah, multiplication, reaction by multiplication on
Yeah.
vectors.
Yeah.
So for CN or yeah. Okay, so now actually I didn't write it. I just was thinking.
So maybe let's try to do it together.
So now what is code?
Okay, so well, maybe you already did a lot. So we proved that GLNC is reductive.
Yes.
And we proved that if we know that UN is reductive, then SUN is It's semi-simple, right?
So we need to show SUN is semi-simple now?
No, we would like to show that UN is reductive, right?
SUN is reductive.
Mm-hmm.
So if we show that SUN is semi-simple, then
Oh, yeah.
And then
yes,
also,
Yeah,
This
yeah.
can be shown because if we consider the trace form
yes.
UN,
Mhm.
and that form is non-degenerate.
Okay, can you show that?
Show that it's not degenerate.
Yes.
Okay, so then,
Okay.
You just write
Yeah,
this.
I didn't do the computations. I was.
yeah, so maybe,
Okay.
So again, we want to show that S. I just saw some
yes, okay.
like some theorem that really my mind is.
Yeah, thank you very much.
I guess it's will help our situation is if we have some real algebra
Yes.
and we do the complexification, and if it is semi-simple, then this guy is semi-simple. And how we show it, it's we can use the Cartan criterion.
Yes.
This guy is semi-simple means the killing form is semi-simple, and the killing form
It's
is
non-degenerate.
non-degenerate, and but this guy is non-degenerate, and this guy is non-degenerate. It's same thing.
Yes.
So
I agree.
they are semi-simple, semi-simple. So I think this can be used to prove this.
Yeah. So if you know for C, then you know already for R, and the other way around. Right. This is a good comment, useful. Yes. But how do you prove that UN is reductive though, or SUN is semi-simple? We need just one of two, right? We need.
Complexification of SUN is SL.
Ah, okay, yes.
And
That's a good. Yes, yes.
First, I consider these, and if the entry is complex number, and we use a tautological representation, and then the matrix form of it will be. And my V is K. And we just, to verify that this form is non-degenerate. And what does it mean? For x, I mean, if x is not 0, and I can find some y, such that this is not 0. So this means this is non-degenerate, right?
So yes.
Yes. And element here is x star. Okay. And we just write down these things. And this is we just use this property.
Right. It's defining actually property of U.
And
Yeah, right.
these, if we just, this is the matrix form, and we just write it, use the every entry, how we
Right.
can look at it.
Right.
Is a minus. And we got this. And for any x,
What's the under summation? I just cannot read.
ij.
Yes.
Yeah.
Okay.
And we just choose y to be x itself. And the choose y equal to x, it will be, these things will be minus the norm of some number, right?
Right. Right.
The norm of some.
Of ijth element. Right.
And these, since x is not 0, so this whole thing will be not 0, will be negative. So this means this form is totally, it's negative.
Negative definite.
Yes,
Right.
yes.
Yes.
So this is non-degenerate.
this is actually an important computation for the last problem. I mean, in the last problem we have SO, right?
Oh, yes.
Not SU, but it's the same thing. So for SO, maybe you can just write the same thing for SO. Would you please?
If SO, if you just have this will be not the conjugate transpose. It will be
Yeah. So
transpose.
yes.
And if you choose the same, this will be a real number square.
Yes.
It's the same.
Right. So on SO, your killing form is negative definite. Not the killing form, but this. Yes, the trace form of.
Yes, and recall the theorem in the lectures.
Mm-hmm.
If we found a non-degenerate invariant bilinear form,
Mm-hmm.
the G and G will be reductive.
Right.
Yes, and so UN, I found the
Mm-hmm.
form of
Mhm.
UN, so UN is reductive.
Yes, and hence SUN is simple because of what Valentina wrote, right? Because we know the center. SUN is semi-simple, right? But also, as O said, SON is its complexification is SL2C, right? SLNC, right? Yes. Did we solve everything here? Yeah, I think so. Any questions? Comments? Suggestions?
I want to ask, because this was in the book of previous, so
Yes.
if we found in a book or something.
You can use it. Yeah. Just no. Yeah. So a lot of this stuff is standard. Of course, it appears in books, and I mean, yeah. So 3.2,
Yeah.
we have some volunteers, right? Okay.
What I want to prove is that if we have, let me check, a simple or a semi-simple, on a simple, the algebra, if we have two non-degenerate bilinear invariant forms, then these forms can differ only by a constant.
Mm-hmm.
So, and the formulation of the problem well, it is natural to try to apply the Shor's lemma here.
Mm-hmm.
So I remind that by the Shor's lemma we have, like if we have by the first Shor's lemma the following, so we have two irreducible representations over the same space V.
Mm-hmm.
So P1 V and P2 V. And if
So the same space V has two different
yes. No,
representation
okay,
structures.
you
Okay.
can change like V to V1 and V2, and then we have like just two parts of this, one of which is just.
Yeah. Okay.
Wait.
Yes.
So, and if we have an intertwining operator phi, such that the following diagrams commute, then a phi is proportional to the unity. So phi is lambda I, and lambda belongs to the base field. Right?
So your representations should be
V and W.
no V is a,
V is it's the same space, but like if you had two different spaces, then depending on the dimensions of these spaces, you would have either this or zero.
Yes, this is short.
yes.
Like I just formulated the first part, but because only the first part we will need. So we have.
Yeah, so we need the statement, right? So if we have an isomorphism of representations, then it's a scalar operator. So that's what it says.
So another thing we have is the Ritz representation theorem, which says that if we have like a linear form on a vector space, so for every element V hat that belongs to the dual space, and for a bilinear non-degenerate form B, there exists such X that belongs to V that like V equals D of X. This is the Ritz representation theorem, and it's unique.
Yeah. Okay.
So, what do we have here? Suppose
So
we
this
have
is unique for non-degenerate.
Yes.
Right?
So what do we have here? Suppose we have two different forms, two different bilinear non-degenerate forms B1 and B2. And suppose we fix the first argument. Since this, when we fix the first argument, I state that this is a linear form, and hence there should be such a vector, like there should exist such linear transformation phi, that phi x. So by acting like this, in this way, we should obtain this. And this will be our intertwining transformation.
Sorry. So the last statement, can you repeat, please? I'm kind of didn't follow.
So I have.
So suppose you have two forms,
Yes.
right?
And I fix.
Fix the first argument.
The first element.
Yes. Okay.
Now we have one form, right?
Yes.
So this one form can, since both forms are non-degenerate, this one form can be represented in terms of this other one form, but we should act by we should transform the vector. And there is a unique transformation, and we can choose a unique linear or not even unique. We can choose a linear transformation, which would transform this vector to the corresponding vector.
No, it is unique, right?
It is unique up to a constant. That's what we are going to prove.
But if you fix two forms and you fix x, I think it should. Yes. Okay. But at least so.
I think for now it suffices that this transformation exists.
Yes.
And it is linear.
Yes. So what is said is that right. So this is a linear form, right? And consider what's called Ritz representation for with respect to B1, right? So there exists. So using this, there exists y, right, such that B1 y dot is exactly this form here, right? Now we would like to see that y is linear, where there's
we can choose such a linear transformation. Obviously, if you have two vectors,
in a vector space,
Mhm.
the general linear group acts on this vector space transitively. So it is not a problem to choose some transformation from the general linear group.
But you want that after you make the transform, it's the same form.
So you see, we by Reed's representation theorem, such a vector that belongs to V exists.
Yeah. So you have
So,
a map
see-
like this, right? You just need to see
Yeah, I mean-
that this map is linear.
But he applied Reed's theorem to both forms.
No,
So
once again, I claim that there exists. I can just.
yeah, you can choose that, and
Mhm.
it defines a new form. What you want that
So
is the same.
imagine
Like-
this is some y, okay? But since general linear group acts on V transitively, you can choose such an element of general
Yeah,
linear group
I
that
agree.
this element acting on X equals Y,
Yeah,
right?
I agree. I mean,
Yes, but it also should not depend on X. Right.
Dependence on X we will treat later.
Oh, okay, then no complaints.
Okay, so
But you can also just see that y of x is just a linear map.
probably, yeah, but that's not.
That's actually kind of obvious, right?
Okay.
And then this is the linear transformation.
I would let this skip the proven the constant, proven the constantness. I don't know how to form an
Okay,
adjective. So this part I just say that it's obvious. Because it's not obvious to me, but I'm glad that it's obvious. So anyway, and now we need to find this pair of transformations. And since our Lie algebra is simple, the joint representation is irreducible.
Irreducible representation, yeah.
So we can act on. We have the following diagram. So here we have b1 of x. Here we have phi, b1 of phi x. And here we have, so we act by the adjoint representation. So for the adjoint representation of an element k, we have b1 of kx. And here, and now we remember that our form is invariant. So I can write it like this. K x, and here is some other element, right? Since our form is invariant.
Right.
So, and then act by phi, obtaining b1 phi k x. At the other hand, if we act by adjoint of k here, we obtain b1. So we can. Do we need it actually? No, we don't. We have k phi x. Right? And now what we want to prove is these two are the same. And then we would have proven the applicability of Schur's lemma, and by applicability of Schur's lemma we would prove that phi is proportional to unity. And this thing we prove by linearity. So by linearity of the Lie product of the not Lie bracket, like how it's called, of the linearity of the bracket.
So your V actually is coadjoint representation, right?
Yes. here I have phi, phi kx, and here I should have k phi of x equals b1 of like phi kx by linearity of the bracket, because this is linear operator. And just moving the bracket here again, we have the same, and also factoring out the linear operator, we also have
let me see. So from here to here.
Here I have just like I use the linearity of the bracket and the fact that this is linear operator. And here this again plus plus I move the bracket using the invariance property.
Yes, but in the commutator you have so phi is linear, that I agree.
Yes.
But again, why? I'm not sure that.
If you have like the linear operator acting on a commutator, you can factor it up, right? Because this operation, the brackets, this operation is linear.
I don't know how. Why? So you have. So what it's written here, right?
Like these two are the elements of the vector space, and this is the operator acting on this vector space. And this operation should be linear in this vector space.
Right. But what is... I'm sorry, I'm a little bit confused. So your x and y, they are elements of what again?
X and y are
Elements of G.
Of G.
Yes. So, right. So x and so this is just bracket in G.
Yes. This is a different kind of element. This is not an element of of G. This is an element of and V, where V is the base.
Is G.
Yeah.
Or G. Yes, G. Okay. I agree. But how to see if, okay, from here to here, I don't know.
Like this?
Yes.
Just, for example, just consider action on the basis.
Right.
And then like, okay, they have an operator. And they have some x, and we have some y, and we expand the sum using the linearity of the bracket, and then just like the action of the action on each element of this sum would be the action of on like the whole bracket. Just
No, you kind of replacing bracket with so linearity means that you can kind of switch sum with your linear operator. You're not using. Yeah, I don't know how you can do it with bracket. I don't know. Do you understand what's going on? I mean, okay. No, I'm just trying. Just would see that this equals to this.
I'm also not sure how to change from side the operator inside the bracket. Is correct?
Yeah, I don't know how.
So okay.
So it's linear. Doesn't have to do anything with the bracket itself, right? So bracket's linear, of course. Linear operator is linear, but how? I don't know.
Wait. again, we can decompose. Okay, let us write.
So maybe some
let us
details.
Use yet another notation.
Okay.
Like here we have xi, and this is in turn equivalent to. So we need to introduce the
Structure constants.
yeah, the structure
Okay.
constants.
Sure.
So
Cij, xy and yj, Cij.
yeah, I need to understand.
But you need not x and y, just x and x. Right? So you just fix one basis, right? X1, xn.
Yes.
You work with this basis. So your xi, xj
No, I mean these are the components of.
is Cij, k, xk. So these are your structure constants.
Yes. And so like the bracket will equal. I think. Okay. C I J. Oh no, C J. Oh, this index should be K. C J K. Wait, how? There should be a way to write this down in components, not.
So we can use things in our lecture today. We already proved this.
Yeah, we already proved. So what we are proving? We are proving that B is that actually this, right? X to this is an isomorphism of representations. But this we did today on the lecture. Okay, very good.
Then by Schur's lemma, it's just
So by Schur's lemma, if you have B1, right? So for every x, right? B if you have B1 and B2, right? So by Schur's lemma, it follows that for every x, B1 dot x is C B2 dot x.
that's all.
And for dot, we just can plug in everything. So for every x and y, we have this. So today on the lecture, I proved this problem. Yes, okay. And then I guess this is what you're trying to do, but I think so. This is some adaptable step. I don't know. So this kind of makes me.
Well,
Maybe I just don't understand your notations.
I don't see what does it have to do with notation. It's just like.
But I'm not sure if you have just some linear operator.
Yes.
I don't know, phi. It's completely not clear for me that that this equals to this. So I understand what's written on the left, I understand what's written on the right. I don't understand why this equals to this.
Okay, I can check it in like in a different. I can check this later. I assumed this for evident because of the linearity of the bracket.
And why it's not x applied to ly? Is this the same? I don't know. It's kind of not. I don't think it's true. Yeah, I don't know. Yeah. Okay, let's move on. But I think you're doing the same thing I kind of did in the lecture. Just the main idea, I agree, it's Schur's lemma. And yeah, so we kind of. And there's a second part.
The second part is
So maybe somebody else would like to do. So yeah.
And for the second problem, we do like this. And since we consider SLN, and we already know this is simple, right?
Yes.
And by Cartan criterion theorem, this is equivalent to KXY is non-degenerate, right?
Yes.
Okay. I want to use the conclusion in problem 1.
Mm-hmm.
And what I need to do is I want to find another non-degenerate bilinear invariant form here.
Mm-hmm.
And this is just the principle. I consider this. And I claim this is a non-degenerate bilinear form on SLN.
Yes.
And the invariant, the things that this is invariant, I think we already proved in the lecture.
Yes, we did.
Yes. Yes, just by the cyclic of the trees.
Yeah.
I don't want to state it again because we already proved this.
Mm-hmm.
I want to state that this is non-degenerate. Why so? Because non-degenerate is equivalent to, by definition, is this. And if this is equal to 0, this means it's non-degenerate. Right. This is just the definition. And for any x here, and we choose, we follow the same thought. We want to choose something to, for any x is non-zero, we want to choose something, some y, some special y, to make this form is non-zero.
Mm-hmm.
Okay. I choose y equal to Eij. I is not equal to j. As we said, this is a basis. This is one of the element of the
Yes.
inner basis.
Yes.
And we compute this. And what we got will be xji.
Mm-hmm.
Yeah, x is any matrix, and this is just with ij place.
Yes. Yes.
What we will get is xji, and you can see that we choose different ij, means if this is equal to 0,
Mm-hmm.
I mean, if for this equal to 0, this means that ji equal to 0, and we have no restriction on ji, just I is not equal to j. So our form for x will be only the diagonal things, right?
Yes.
And then we just choose y. We just choose this, and this is the remaining base of SLN.
Mm-hmm.
And we also compute this. And it will be this. And since we know x is also in SLN, it's traceless. So, and ij can be go through from 1 to n minus 1. And then we know x, the diagonal will also be 0.
Yes.
So x, it means x is 0.
Yes. So it's non-degenerate.
So it's non-degenerate.
Yes. Okay.
And what we should do next is to compute And we use the conclusion in the problem 1. Say that these two non-degenerate invariant bilinear form will differ by a constant. Okay, so maybe we can state that.
So we just need to compute this constant.
Yes.
For that, we just need to check the value.
Now we should compute what is C.
Yes, we just take some x and y, plug in to the left, to the right, and then we can compute C, right?
Yes, yes.
Okay, so what would be your choice of x and y to compute it?
I just chose x equal to y and x,
Right.
x equal to, for example, E12. E11 is not in SL. And I choose this. And so, well, no, I didn't choose it. I really choose it. This is
Okay.
this is in SL. And so consider all the bases in SLN. And we just need to compute the bracket. So I should also say that the representation actually is the adjoint representation I choose.
Right. So you then you write add x, right, in some basis.
Yes, yes.
It's a diagonal. It's first
Yes,
of all
this
it's
is
diagonal.
diagonal.
And what stays on diagonal? So then you need to compute what stays on diagonal.
Yes. And this is what I will do next.
And diagonal is n square long, right?
And you plug in x is this, and you will get the formula.
Because add x is n square by n square matrix, right? Because it's a transformation of n square dimensional space, which is
But we know the
n square minus 1 because it's a length here.
we know the highest weight of this representation, and maybe we don't need to compute again.
That is true. That is true. But do you know all the?
But we don't need the E1 and E minus to how it acts on another things.
But you need the trace of this matrix, right? So you need all the eigenvalues.
Yes.
So you need all the weights, kind of, not only the highest one.
And what we are doing is there is an easy way. So the easy side and the hard side. Easy side is use this formula, and I choose x, y equal to x, and the trees. This is easy to compute. This is
2.
very easy, 2. And what we do is by the definition of the Kaling formula use, and you compute the left hand side. What is left hand side? Since we know this is 2, and we compute the left hand side, then we know the C. And by this formula, and we discussed, if I equals 1, j equals 2, and what we will get is in the basis E12, we will get the 2 E12. The right hand side is 2 E12, and the basis which we choose is E12. And for I equal to 1 and j greater than 2, and since I is not equal to j, and j greater than 2, we'll get basis with I1j, and the final get is I1j.
Mm. Mm-hmm. Mm-hmm. Mm-hmm.
And what we should do is to compute the trees of this diagonal matrix. What would you is just count how many these coefficients appear in our matrix. And these you can see we have a 4 and 2 squared. Since we just have this one. And here we have how many 1? This is 1 squared equal to 1, and we have j goes from 3 to n. So there's n minus 2, 1. And about these, there is minus 2. Minus 2 squared is 4. And we have 1, 4. And about these, how many is n minus 2, 1?
So let's just write down what you're computing. So you're computing trace, right, of at h1 at h1, right? H1 is this guy, right? And what we got is that we got a matrix of at h1 in the basis eij, right? In the basis eij, this matrix at h1 is diagonal, right? Add means just take a commutator and see what value will come out, right? So in this basis, your matrix is diagonal, right? And what stays on this diagonal is actually the eigenvalues, right? So the eigenvalues, they are here. So 2, right? 1 here, negative 2 here, right? So since we then multiply matrices, we should take this value squared, right? So that's what we're doing, for example. You take this 2, take this value squared. Then so here is just one eigenvector with such eigenvalue, right? So we just counted, it's 4. Then plus, we count this line, right? So how many matrices, how many elements eij I have with such condition, n minus 1. They all will be eigenvectors with eigenvalue 1. So it's actually 1 times, or is it n minus 2? J greater than 2. 1 times n minus 2. So 1 square is 1, so it will be n minus 2 times 1 squared. Then I look here, negative 2 squared, right, is 4 again. And I just have one matrix here. And then I continue in this.
And we will have n minus 2, 1. Oh, also have n minus 2, 1. And here we have n minus 2, 1. And we have
1 or negative 1 doesn't matter because I take square.
Okay. And now these are 4. And it remains to see that it's actually not all the bases. There are some bases EII plus E, I plus 1, I plus 1. And it's easy to prove that x, the commutator of x and this is 0. So it gives us nothing for the rest of the bases.
Yes.
It doesn't give us a 0 eigenvalue.
Yes.
The final answer here is our left-hand side. This is 4n. And we want to compute this is 2.
Right.
So our C is 2n. So this proves our formula for Killing for SL.
Yes. So maybe let's go to, since nobody really, only ideas for 3. So maybe, so Abner, you said that you solved 4, so maybe you can show us 4 then. Yes.
like the idea is to use the fact that if a form is degenerate, then it's you can again fix the first element of the bilinear form to produce a one-dimensional representation. And the kernel of this representation will be not zero only if the form is not degenerate.
Okay, so
And so the kernel, there is an analog to the group homomorphism theorem that the kernel is an ideal. The
yes,
kernel-
yes, and you need to prove that it is solvable, therefore it is zero.
Yes.
Yeah, that's an idea. But let's listen to Abner. Yeah.
It's to prove that the radical of the algebra, any Lie algebra, it's equal to the orthogonal of the commutant. So, yeah, okay, to prove this contention, it's like, okay, we will take the commutant, the orthogonal of the commutant.
Sorry, what is this symbol you have written on the left? No, on the left.
This
Yes.
contention, like when you write this, but
Ah,
The
oh,
other
I'm sorry,
side.
it's just...
okay.
Yeah, this way inclusion, yes. Yeah.
Okay, we take
With
theta.
frame.
Together
With the
this
frame.
with this angle, it looks
Yeah.
like
Something else, yeah.
like a Korean, like a Korean, like a symbol of a Korean alphabet.
Okay. Okay, we take this and we're gonna suppose it's different to the radicals. Okay, so we're gonna prove that this is the killing form. It is to use the Cartan formulas. So the killing form evaluated in this commutant of the Lie algebras and eta, that is the orthogonal. This is 0, right, for definition, because this is orthogonal complement and this is the orthogonal to that. Okay, so in particular, what will happen? Eta, it's contained in both in the Lie algebra. So, as consequence, we have that the killing form evaluated in the commutant of eta with eta, it's also 0. And by Cartan's formula, we have that then eta is solvable.
Yes.
And by, as the radical is the maximal, it's solvable, so eta is contained on the radical of the, yeah, I think this, I just wrote. Okay, so we have that contention.
Yes.
I had some problems for this. I didn't know how to finish it. I thought it was to use the other Cartan's formula. No, not formula, Cartan's criteria. Okay, so to solve this, we have to check that any element in the radical is also orthogonal to the commutant. So we take
Yes.
by the criteria of Cartan, we know that this happens. This is right. But we want to prove this. So we need, okay, when one of these entries are, one is the radical, as the radical is also an ideal, we came back to this. No, sorry, no. That was also like, okay, yeah. this is 0 only
So hint use invariance.
variance. Ah, okay, yeah.
Right. Right. So
This is no, but this is more related with reductive. No.
This is the subset
Yes.
of radical.
Yeah, it should
I also consider
be. It's in the radical also.
so this thing acts by 0 in every
Yeah.
every irreducible representation, right?
Mm-hmm. But
Which one?
Which x 0 by?
You mean the radical?
No. This thing.
but, about linear algebra with
Yes.
Excuse me, why?
It's the same.
we drove it.
That's that.
Okay, I forgot.
Yeah.
What about
Some number of lectures ago. So therefore, so what is Cato?
It's a killing. It's
It's not a killing form. It's a trace form, right? Yes, it's killing form. Yes. Okay. Yes.
So,
Sorry.
exactly, is it the new red? Like, is this commutator the new red of G?
The what?
The new radical.
It is contained in new radical. Yeah. That I can say for sure. I think it's true what you're saying, but don't quote me. I think it's
Because like it is the definition in.
yes in this book. Yeah. I mean.
No, when we prove it on last seminar, it's in here.
Yes, yes, but is it exactly new? That's the question. So I'm not particularly sure.
So
I
there is
Not
no
exactly.
where it defined in this way.
Not exactly the it's contained in the
okay, we are kind of deviating. So let's just try to finish the problem. So this is killing form, but the killing form is trace add something, right?
Yeah, in X in.
Add something, right? Well, it's not equality because we have sets here and here it's element. Yes, this one is in G, this one is in. So what I claim is that we also saw this trick in the lecture. So of course, the adjoint representation might not be reducible, right? But it has a composition series. So let's remember what was the composition series. Yeah.
The vector spaces and the quotients are reducible.
Quotients are irreducible, right? So we have like a sequence. So that we. So what I claim actually is that so this is a killing form, right? What I claim is that right. So this is sum. So killing form of x and y is sum over right traces. So what I would like to say that it is sum over b wi's. So this is a trace form of a representation wi of x and y, where wi's are the following. This form composition series of the adjoint representation. So I have w1 inside w2. Actually, not even w's, but v's. So I have V1 inside V2 inside so on. And the last one is G itself as a representation. It's a joint representation. And Vi quotient by Vi minus 1 is, this is what I call Wi. Is irreducible. Right? So the killing form is actually the trace form for the representation G. Right? But since Y, but this thing is what? It is trace over W, rho Wi of X, rho Wi of Y, right? But since Y lives in where? In here, and Wi is irreducible, so this is just 0. So every element here is 0. So therefore, this is exactly what we wanted. That radical, if I plug in inside so something from radical here, it's 0. It means that radical is inside orthogonal complement to this one. And this equality, we proved, we did this on lecture.
Yes.
Again, these pictures with blocks. Right, so you have invariant subspace, you have this block.
Yeah, what we use is to decompose the space in like.
Yeah. So you have invariant subspace, right? So if suppose you have just two of them, so V and V1, right? Then V1, then your rho V looks like this: rho V1 here, right, of some x, right, and so, and then you have W, and then you have W, which is V quotient by V1.
But then
So
it's not important that this was the adjoint representation, or when we use the adjoint representation, it's for any representation?
this is for any representation, yes.
Okay.
The importance of this, I
This
think,
was to this,
yeah, because you used Cartan's criterion of solvability. So for this, this is important
that's
for
what-
healing
for
form.
this context.
The other way, we're just using invariance, and that this is acting by 0 in every irreducible representation. But this form is just a sum over trace forms of over irreducible representations, right? So we have this.
Okay. So we have like that contention.
Yes,
or-
both way containment, inclusion, right? So therefore they equal. Should I repeat something for those who is lost? Christina,
Oh, you can, but I don't know.
you can try.
This was a
So
task.
are we running out of time?
Yeah.
Ah, okay, that's why everybody's so sad.
No,